Hello, today we're going to talk about the Proterozoic. Okay, the Proterozoic is the second of two, or you could even say the third of three eons in the Precambrian. And you will need to know the dates that divide the Precambrian up into the different eons. So the beginning and end dates for the Archean, Proterozoic, and even for the Hadean. Okay, now the Proterozoic eon includes 42% of all geologic time. And the Phanerozoic eon, which comes after the Proterozoic, includes only 12% of all geologic time. However, we're going to spend pretty much the rest of the semester talking about the Phanerozoic, because this is where all the so-called interesting stuff, such as the building of Pangaea, the breaking apart of Pangaea, and the evolution of most of the animals that we see today, this is when all of that occurs. Okay, now the Proterozoic can be broken up into three different eras. Now, I do not expect you to know the dates that separate these different eras, but I do expect you to know the sequence in which they occur. And you can pretty much tell the sequence by looking at the prefixes on these different eras. So Paleo, for Paleoproterozoic, paleo means old. Meso, as in Mesoproterozoic, meso means middle. And neo, as in Neoproterozoic, neo means new. So the Paleoproterozoic is the oldest era in the Proterozoic, the Mesoproterozoic is the middle era, and the Neoproterozoic is the youngest of the eras. At the beginning of the Proterozoic, which was 2.5 billion years, we see extensive oceans, lakes, and streams. By this point, we also have an ozone layer which reduces the amount of UV radiation in the atmosphere. The only life in the oceans is bacteria, and volcanism and tectonic plate movement is still very intense, although not quite as intense as it was in the Archean. We do see stromatolites in the Proterozoic. They first appeared back in the Archean at about 3.5 billion years, and they have been linked to the increase of oxygen in the atmosphere. So if you remember what we talked about in class, we discussed that there were three different ways that the modern atmosphere was built. The first was by outgassing from volcanoes and rocks. The second was by photochemical dissociation, and the third was by photosynthesis. And the photosynthesis was from cyanobacteria, which built stromatolites. Now, at the start of the Proterozoic, we have 1% oxygen, and by the end of the Proterozoic, we have about 10% oxygen in the atmosphere. Okay, so what evidence do we have for a lack of oxygen in the atmosphere in the Archean and the Proterozoic? Well, we see different minerals which are only stable when there is no oxygen in the atmosphere. And examples of these minerals are detrital pyrite and uraninite. Both of these minerals are only found in oxygen-poor environments. Another indicator of the appearance of oxygen throughout the Archean and the Proterozoic are banded iron formations, and that's what we're going to talk about a little bit now. So what are banded iron formations? Well, they're alternating layers in which we have siderite, which is an iron carbonate, alternating with hematite, which is an iron oxide. And you can see some of those alternating layers in this picture on the left. Now, the precipitation of these banded iron formations is probably linked to the first abundance of oxygen. 92% of all the banded iron formations were deposited between 2.5 and 2 billion years ago, and 90% of the world's iron ore, which is 1 billion tons mined yearly, comes from these deposits. How do these banded iron formations develop? Iron and silica were dissolved in water from deep hydrothermal vents. Now, hydrothermal vents are found along mid-ocean ridges. Hot solutions from these vents originate when seawater seeps into fractures along the ridges and encounters very hot rocks. Once heated, the water can then dissolve iron and other elements, and then this rises up to the sea floor. When this solution containing iron came out on the sea floor, it reacted with carbon dioxide in the seawater. And the reason why it reacted with carbon dioxide in the seawater was there was no oxygen in the seawater to react with the iron. So the iron reacts with the carbon dioxide to form siderite, the iron carbonate. Now siderite only forms in the absence of oxygen, which is why we know there was no oxygen in the seawater at this time. So cyanobacteria were present on Earth and they were photosynthetic. So they could have been producing oxygen like you can see in this picture here. And that oxygen would have been dissolved in the seawater that would then have interacted with the iron coming out of the hydrothermal vents, and this time hematite would be produced. Hematite is an iron oxide and it forms in oxygen-rich environments. Okay, now hematite would continue to form until all the oxygen has been used up. And then at that point, carbon dioxide would be left in the water. So the iron would then interact with the carbon dioxide and form siderite, which means that we would get these bands of siderite forming and then hematite would form. And then siderite would form again, and then there would be oxygen in the water again. The iron would interact with the oxygen and form hematite. So you can see we would have all these layers or bands building up, hence the name banded iron formations. Now the source of the oxygen producing the banded iron formations came from the dramatic increase in the abundance of stromatolites at about 2.3 billion years old. Now lots of oxygen was required to oxidize all of the iron coming out of the hydrothermal vents, and until it was oxidized, levels of oxygen in the atmosphere did not increase. Now once that iron had all been oxidized and locked away in the banded iron formations, oxygen could finally start to build up in the atmosphere. Okay, this picture is from one of the 2 readings I've asked you to do. It's from how the air we breathe became breathable, and it just shows you that we have indicators of low atmospheric oxygen, which are our detrital pyrite, our uraninite, and our siderite, and these continue until about 2.3 billion years. This picture also shows that we have 2 peaks of oxygenation. We have what's called the small oxygenation event at 2.9 billion years, and then we have the great oxygenation event that occurs at about 2.4 to 2.3 billion years. Cyanobacteria were already present at this time because we see our stromatolites first appearing in the fossil record at about 3.5 billion years. But we think that these oxygenation events were linked to the first appearance of larger land masses, because at this time we would start to see an increase in weathering of rocks, and this would pull carbon dioxide from the atmosphere, causing cooling on land. And once the cooling starts to occur, cyanobacteria can start to take over and proliferate. Now, the first oxygenation event that occurred, we think this process happened, but the continents weren't quite large enough, so it petered out. And then larger land masses were more present at 2.4 billion years, and this oxygenation event was able to sort of pick up steam, as you might say. Soon afterwards, we see these rocks called red beds appearing. So red beds are reddish continental sedimentary rocks. They're sandstones and shales. The color in these sedimentary rocks is caused by the oxidation of iron. So they formed soon after the banded iron formation, starting at about 1.8 billion years. And the appearance of red beds indicates the presence of more atmospheric oxygen. So we probably have more than 2% oxygen accumulating in the atmosphere at this point, and these red beds increase in abundance in the Proterozoic and are common in the Phanerozoic. So we see little or no detrital pyrite or uraninites after about 2.3 billion years. And at that point, we see more red beds appearing. Okay, now if we look at our Archean rocks, in the Archean we have greenstone belts and granite gneiss complexes that formed into cratons. Most of the rocks from the Archean are metamorphosed. Sedimentary rocks are rare, mafic and ultramafic volcanic volcanics are abundant, there are rare primitive life forms present, and a few and localized banded iron formations. Now in the Archean, what do we know about the size and position of the continents? Large continental landmasses did not originate until late in Archean time. In the Proterozoic, we see fewer greenstone belts and granite gneiss complexes developing. We see fewer mafic volcanics present. So why do you think that is? We also see that most of the rocks are not metamorphosed. Sedimentary rocks are more widespread. Banded iron formations are abundant and widespread until about 2 billion years ago. And we finally see eukaryotes and multicellular organisms appearing. So what do we know about the size and position of the continents in the Proterozoic? One of the highlights of the Proterozoic is that the supercontinent Rodinia, which is the first supercontinent, forms.